All right, let's talk about something that sounds like it was pulled straight from a science fiction movie. We are going to be talking about zapping batteries with high-powered lasers, all in the name of ultra-fast charging. It's pretty wild stuff.
You know the feeling, right? We've all been there. You're staring at that little blinking battery icon. You're literally chained to a wall, just waiting for your phone, your laptop, maybe even your car to get back to 100%. But what if that wait time could be, basically eliminated? Well, that's the promise we're digging into today. Okay, so to understand this awesome new solution, we first have to get a handle on the problem itself. And it all comes down to this really promising type of battery that, for all its amazing qualities, has one major flaw: a built-in speed limit.
So let's just break this down. The battery in your phone, it probably uses lithium cobalt oxide. But there's this other kind, lithium iron phosphate, or LFP for short. And LFP batteries are a huge deal. They're already in EVs like the standard range Teslas because, look at this. They're way safer, they last twice as long, and they're cheaper. They seem perfect, right? Well, not quite. Look at that very last row, the conductivity. It is shockingly, almost comically low. We're talking hundreds of thousands of times worse. And that, right there, is its Achilles heel. This super low conductivity leads to what scientists call poor rate capability. So, what does that mean in plain English? It's basically the battery's ability to not totally fall apart when you try to charge it really, really fast. Think of it like this: trying to fill a giant swimming pool with a tiny little garden hose. You just can't get the water in fast enough. That is the exact problem with LFP batteries. They're safe, they're cheap, they last forever, but man, are they slow to charge. So how do you fix that? How do you turn that little garden hose into a massive fire hose? Well, this is where it gets really, really cool. A team of scientists in South Korea came up with this idea. What if we used a precision laser to basically build energy superhighways inside the battery itself? Okay, to really get this, picture the inside of a regular LFP battery. You've got all these lithium ions. They're the little guys carrying the energy. And they're all trying to move across this flat, two-dimensional surface. It's like a single-lane country road at 5 p.m. on a Friday. Total gridlock. You get traffic jams, and the flow of energy just slows to a crawl. That's the bottleneck. And here is the aha moment. This is the fix. The scientists took a nanosecond laser, we're talking incredible precision here, and they carved a specific pattern of microscopic grooves right into the battery material. And what this does is create a brand new three-dimensional network. All of a sudden, you have all these shorter, faster paths. They've turned that slow country road into a multi-lane superhighway with on-ramps and off-ramps everywhere. The energy can just flow, and it can flow fast. Now, that sounds absolutely brilliant in theory, doesn't it? But, the real question is, did it actually work? So naturally, the researchers set up a really clever experiment to put their idea to the test. So here's what they did. Their process was super methodical. First, they made a totally standard flat LFP cathode, our baseline. Then they brought in the laser to do its thing, carving those tiny patterns. But here's the key. They didn't just try one design. They systematically tested all kinds of different groove shapes and different spacing to find the absolute perfect combination. Then they took those new 3D cathodes, built them into actual batteries, and tested their charging speeds. The two main things they played with were, first, the groove shape itself. They called it the aspect ratio. Basically, were the grooves going to be deep and skinny or shallow and wide? And second, they tweaked the spacing, the pitch distance. So how close together should they carve these little superhighways? The whole goal was to find that perfect balance. But as it turns out, it wasn't as simple as just carving as many tiny roads as they possibly could. They ran smack into a really critical balancing act, a fundamental trade-off between how fast you can charge and how much energy the battery can hold in the first place. This quote from their paper really just nails it. Carving the grooves, well, that improves the rate capability. That's our charging speed, because you have more surface area for the ions to move around. Great. But, and this is a huge dot, it also reduces the energy density, because you're literally vaporizing the material that actually stores the energy. So you're drilling for speed, but you're risking draining the tank. And here are the cold, hard numbers on that problem. Look at this. When they used shallow grooves that were far apart, they only lost a tiny fraction of the material, less than 1%. But when they got really aggressive, deep grooves packed super close together, wow, they lost almost 31% of the material that holds the charge. That's a massive hit to the battery's total capacity. So, After all that testing, what was the actual payoff? Well, this chart here shows you everything. This is the performance during a really fast charge, what they call a 2C rate. Think of it like trying to charge your entire electric car in just 30 minutes. It's aggressive. And under that kind of pressure, the standard battery just can't keep up. Its capacity takes a nosedive. But the laser-structured battery that they optimized, it held onto its charge much, much better.
And here is the magic number. The absolute best design, the one that hit that sweet spot with shallow grooves, spaced far apart, it held its capacity 6% better than the standard battery during that fast charge. Now, I know what you're thinking. 6%? That doesn't sound like that much. But in the world of battery science, getting a performance boost like this at high speed in a material that's already safe and cheap, that's a really big deal. It's a significant step forward.
So let's zoom out. Let's connect all these lab results to our world. What does a breakthrough like this actually mean for the future of charging and for all the devices we can't live without? Okay, so let's just wrap it all up. Here's what you really need to remember. First, LFP batteries are awesome. They're safe, they're affordable, they last a long time. But their one big problem is that they're slow. Second, we now know we can use lasers to carve these incredible 3D superhighways inside them to speed things up. Third, doing this creates a really important trade-off. You gain speed, but you can lose storage. The secret, as these scientists found, is finding that perfect pattern that loses the least amount of material. And finally, this whole technique could be the key to making these great LFP batteries a serious option for pretty much any fast charging need, from our phones all the way up to our cars.
And that brings us to the final big picture question. This research is a powerful proof of concept. So could this kind of incredible, precise laser engineering be the key that finally unlocks that dream we all have of charging an electric car in the time it takes to grab a cup of coffee? You know, based on this research, the future of charging is definitely looking brighter and a whole lot faster.